In this lesson, we're going to look at conditional probability, more specifically dependent events. Conditional probability is the probability of an event occurring given that another event has already occurred. Now with dependent events, the outcome that previously happened will determine what's going to happen next. They will be affected by each other. Mathematically here, we've got probability of A and B occurring is the probability of A times, because of that and, the probability of B not A. Let's take a look at the first example and see what we mean. It says a computer manufacturer knows that in a box of 100 chips, 3 will be defective. Jocelyn will draw 2 chips at random from a box of 100 chips. Determine the probability that Jocelyn will draw 2 defective chips. In order to solve this, we're going to draw a tree diagram. So when we draw our first chip, the chip will either be defective or not defective. And we're told that if it's defective, there's 3 of them out of the total 100. So I'm going to write that probability there. 3 out of 100 will be defective. Well, that means that 97 out of 100 will not be defective. Okay, well that's the first chip. And then for the second chip, if the first one's defective, the second one might be defective, or it might not. And the same will hold true if the first one's not defective. The second one might be defective or not. But what we're trying to solve for is the probability that Jocelyn will draw 2 defective chips. So the first one is defective and the second one is defective. So if the first one is defective, that's 3 out of 100. That's the probability that you'll get that one. Assuming that you're holding that defective one in your hand, how many chips are left? Well, there's only 99 chips left because you're holding one of them. And out of those 99 chips, if you're holding out of those original 100 chips, if you're holding one that's defective, you no longer have 3 defective in the pile, but you've got 2. So 2 out of 99. So to figure out this probability, it's the probability of defective and effective, 2 of them being drawn. That would be 3 out of 100 multiplied by 2 out of 99. The 99 part and reducing the 2 from 3, that's the tricky part. That's where students get confused. But understanding that we're assuming that that first one is defective, so you only have 2 defective ones left, and you no longer have 100 chips in the pile, because you're holding one, you only have 99. So the probability here would be 6 out of 9,900. You can leave the answer like that. If you're checking it in the textbook or with a solution, usually they reduce it, and that would be 1 out of 1,650. Both solutions there are all right. But this is what we mean by dependent events. The second event is dependent on the fact that you've drawn that one defective chip already. Let's try another one. Nathan asks Riel to choose a number between 1 and 40, and then say one fact about the number. Riel says that the number he chose is a multiple of 4. Determine the probability that the number is also a multiple of 6, using each method before. Alright, so for A, using a Venn diagram, we've got multiples of 4, and we've got multiples of 6. Right? So if we look at our numbers between 1 and 40 that are multiples of 4 and multiples of 6, there are some that are both multiples of 4 and 6. So take a moment to fill out the diagram, and I'm going to do that as well. Alright, so I have my multiples of 4 only. That would be in this section here. I've got my multiples of 4 and 6 here. And then I've got my multiples of 6 only here. There's 27 other numbers that I don't have room to list there, but that would be sitting out here. So the probability that the number is also a multiple of 6. So it's a multiple of 4 and also a multiple of 6. How do we figure that out? Well, let's first write that down. This is for A. So the probability that it's a multiple of 4 and 6, well, what's the total here? How many numbers are we looking for the denominator? Now, in terms of the numerator, everyone's saying 3, which is good, because that's these numbers here, a multiple of 4 and also a multiple of 6. But in terms of what are all the numbers, we're looking at what are all the numbers that are a multiple of 4. So you're just looking for these ones. So this is representing your denominator, your total number of outcomes. So how many outcomes do we have there? We've got 10. And that's the confusing part, because in previous questions when we've done a Venn diagram, when we're just talking about the numbers, we're not always looking for the probability. It's easy to identify the intersection, which is what we're looking for here, multiple of 4 and 6, which would be 3. But in terms of what it's out of, you're not looking at every single number in the Venn diagram, because initially they're just saying a multiple of 4, and we've got 10 of those, and then of those 10, how many of them are also a multiple of 6, and that's where the 3 is coming from. Just make a note of that so you remember that for later on. Now, in terms of using a formula for this isn't super intuitive, and if you don't want to use this, that's okay, but I'll put it in your notes and explain it just in case this works better for you. So for B, using the formula we would have is the probability of F and S, which is equal to the probability of F multiplied by the probability, oops, lost the P, probability of S not F. Okay, so if we just look at the probability of F, so that's saying how many of those multiples of 4 are a multiple of 4. Well, that's all of them, 10 out of 10. But how many, the probability of S not F, so the probability of S, we've got 3 of them out of a total of 40, out of the ones that are a multiple of 4, which would be 10 out of 40. And when you divide fractions, that would be 3 out of 40 times, right? When you flip the denominator, that would be 40 out of 10, which would give you the same 3 out of 10 probability. And then when you multiply them, that would be 10 out of 10 to get our probability, multiplied by 3 out of 10, which doesn't change this probability. You end up with, because 10 out of 10 is 1, times 3 out of 10 would still give you 3 out of 10, the same answer that we get up here. I like the Venn diagram better because it's more visual, but this is another way of doing it. Let's take a look at example 3. So this is another question where we're going to be using the tree diagram, and you can see how this comes about. It says, according to a survey, 91% of Canadians own a cell phone. It's nice when they give you the percentages already, because they're already giving you a probability. You don't have to do any extra math with that probability itself. We just have to do more math with what we're being asked for. Of these people, 42% have a smartphone. Determine to the nearest percent the probability that any Canadian you meet during the month in which the survey was conducted would have a smartphone. Okay, now I would anticipate this is quite an old question. Most people, I think, have smartphones by now, but that might be an assumption I'm making here. But we can use this data here. So if we look at the initial data, 91% of Canadians own a cell phone. So I'm going to use that to start. Now it looks like only one piece of information, but it's actually 2. So we're going to look at people who own a cell phone and people who don't own a cell phone. And because they're giving us 91%, well, we know that this is going to be 0.91 if I just put it as a decimal. So what does that mean for people without a cell phone? Well, these are the people who weren't surveyed yet, so that would be 0.09. Okay, having those listed in the tree diagram is quite helpful. Now, because these people who don't have a cell phone, they were not surveyed, we're done with them. Okay, so what's left? Well, of these people, 42% have a smartphone. So of these people, the people who have a cell phone, 42% have a smartphone. So the rest of them don't have a smartphone, so we have to include that too. And again, two pieces of information. The fact that the people who have a smartphone, that's 42%. So the leftovers would be 58%. But what are we being asked to figure out? We're being asked to figure out, determine to the nearest percent the probability that any Canadian you meet will have a smartphone. So they need to have a cell phone, and the cell phone that they have must be a smartphone. So what you're going to be doing is taking both of those probabilities and asking yourself, do I have to multiply them or do I have to add them? Because we're looking at both cell phone and smartphone, we're going to multiply those together. So cell phone and smartphone, that would be that 91% or 0.91 as a decimal times our 42% or 0.42. And doing that math, you'd get an answer of 0.3822. And if you want to change that back to a percent, 38.22%. As a rule, we're going to always remember to round to 2 decimal places, okay? So if you're leaving it as a decimal, that would be 0.38 would be fine. But as you change it to a percentage, you want to have those extra 2 decimal places. So always round your answers to 2 decimal places for these questions. And really, for the whole course, you should be rounding to 2 decimal places as a rule. Let's take a look at another example where we're doing a similar type of question. Hillary is the coach of a junior ultimate team. Based on the team's record, it has a 60% chance of winning on calm days and a 70% chance of winning on windy days. Tomorrow, there's a 40% chance of high winds. There are no ties in ultimate. What is the probability that Hillary's team will win tomorrow? So again, we're going to start with a tree diagram. But how are we setting this up? Well, it says based on the team's record, it has a 60% chance of winning on a calm day and 70% chance of winning on a windy day. So let's start by just saying, okay, the day is either going to be windy or calm. And depending on whether it's windy, they'll either win or lose. And if it's calm, they'll either win or lose. Now, according to the data here, it says tomorrow there's a 40% chance of high winds. So that would be a probability of 0.4 or 40 if you want to keep the 40. So then what's the percent or probability of it being calm that day? And that would be 60% or 0.60. Now it says on a windy day, based on the team's record, it has a 60% chance of winning on calm days and a 70% chance of winning on windy days. So on a windy day to win, that would be 0.70. And on a calm day to win would be 0.60. So again, they're giving us that information here. That's coming from here and here. And then the 40% was there. Right? But again, every time they give you one of these values, they're actually giving you 2 values, because if it's a 70% chance of winning on a windy day, then that means there's a 30% chance of winning on, 30% chance of losing on a windy day. And same with calm. 60% chance of winning on a calm day, that means there's a 40%. How do I know? Because they always have to add up to 100%, or for decimal places, they have to add up to 1. Now, the question that we're trying to solve says that what is the probability that Hillary's team will win tomorrow? There's actually two paths you can take. It could be a windy day and they'll win, so that's going along here. Or it can be a calm day and they'll win. So either or, so two cases, and remember when we have two cases, that or comes into play, which means we're actually adding those two up. So to get a windy day and win, the probability would be 0.4 times 0.70. And the probability of winning on a calm day would be 0.60 times 0.60. If you do the math for that, that would be 0.28 for windy and win, and that would be 0.36 for calm and win. But because we want it to be windy and win or calm and win, either one of those situations, we have to add those up. Let's write that out. So we've already figured out those two probabilities. That would be 0.28 plus 0.36 to give us a probability of 0.64 or 64%. That's it for today's lesson. If you want to take a look at the next page, we have a nice summary of what we learned today. You can have a look through that. Thanks for joining me.